Significant figures, also known as sig figs. Students really struggle with this concept. I need you guys to just memorize the rules on them and get them down now. If you get them down now, you won't struggle all semester, truthfully all year long, okay? Trust me, these are the rules. They are the rules no matter where you go. They're set rules for sig figs. They're not just for my class. They are the rules of sig figs. First rule of sig figs, and again, sig fig just is short for significant figures. They're helping us track the precision of our measurements. All non-zero digits are significant. If you are given a measurement, any number that is not a zero that is written down is significant, no exceptions. So when I look at 5.32, I have 1, 2, 3 sig figs in my answer. When I look at 2,332, I have 1, 2, 3, 4 sig figs in my value. The little SF is just my shorthand personally for writing sig figs. Sounds right out the word sig fig every time. Number 2, if I have a 0 sandwiched between other sig figs, it is significant. I call these sandwich zeros. I call them captive zeros. They are trapped between two non-zero digits, two integers. 502, all three numbers here are significant. This has 3 sig figs. 5002 has 4 sig figs. The 0 here is trapped between a 5 and a 0. So that can confuse students, and I understand that. The 0 here is trapped between a 0 and a 2. Both zeros, though, are trapped between non-zero digits, therefore they are also significant. They are showing me that my measurement is actually precise here out to the 3rd decimal place. Leading zeros are not significant. Leading zeros are all of these zeros before the actual integer starts. A way to check yourself if you're unsure is to put the number into scientific notation. If the leading zeros appear to disappear, they're not significant. If I put this number into scientific notation, I would have 5.32 times 10 to the minus 4. Notice those leading zeros, these 4 zeros out front here, are not present in my scientific notation. That means that they are not significant. So this number only has 1, 2, 3 sig figs. Again, same thing here. If I was to put this number into scientific notation, I would have 5.002 times 10 to the negative 4. So I have 4 sig figs. These zeros in front, not significant. I have 1, 2, 3, 4 sig figs in this value. Final zeros get tricky, and this is where you have to pay attention to what you're doing. Final zeros in a number with a decimal place are significant. I don't care if it comes before or after the decimal place. If you have a decimal place and you have a trailing zero, final zeros can also be known as trailing. They're trailing the rest of the number. They're at the end of that number, okay? So notice here, I have a decimal place. That means that these 2 zeros here are significant. This is like saying I owe someone $5. I owe them exactly $5. I don't owe them $5.25. I don't owe them $4.95. I owe them $5.00 to the penny. This has 3 sig figs. The 5 and both zeros are significant. The second number shown here, 0.05020, the zeros in front are still leading zeros. Leading zeros are never significant. The 0 in the middle here is captive or sandwiched between 2 other numbers, so we know that's significant because of a prior rule. But the 0 here is a trailing 0. This trailing 0, though, is after integers and the decimal place is present. So it's a trailing 0 that's present in a number that has decimal places, but also is after the integers. It is showing me that this measurement is actually precise out to the 5th decimal place. So this number here is also significant, and overall I have 4 sig figs here. The 5 this 0, 2, and this last 0 here all being significant. And 150 with a decimal place on the end. Think about this decimal place kind of like a bookend. It's holding that 0 in place. If I wrote 150, I only have 2 sig figs. This 0 here can drop off. Nothing's holding it in place. When I write 150 with the decimal place though, this decimal place is holding that 0 into place. It is a final 0 in a number with a decimal point. So here I have 3 sig figs. Final zeros in a number with no decimal place are ambiguous. What that means is they're not significant. If you want them to be significant, you have to give us more information. But as written, they are not significant. So here, only the 1 and the 5 are significant. I have 2 sig figs to this measurement. When I write the number 2000, all of those zeros there are not significant. They're ambiguous. There's not a decimal place listed. So this only has 1 sig fig in the value, 1 sig fig in its entire value. Often scientific notation is required to actually represent the correct number of sig figs. So let's go ahead and write this number. Sorry, I need to move the screen so I can write on it. Write this number to 3 sig figs. If I tried to write this to 3 sig figs, that would be 1, 2, 3, but I can't lose the fact that it's 1,500. I can't just drop that last 0. If someone owes me $1,500, I want 1,500. I don't want to just drop the 0 and them owe me 150. That doesn't seem right. So I'm going to put it in scientific notation to emphasize the sig figs of the number. If I write 1.50 times 10 to the third, that is the same numerical number. It's still 1,500, but notice now I have 3 sig figs listed. Let's try again, doing it with this one to 2 sig figs. Here I have the number 9,000. Again, 2 sig figs, I can only have these first 2 numbers be significant because the integer, the non-zero number, is always significant. I don't want to just drop those 2 zeros because again, if someone owes me $9,000, I want 9,000. I don't want 90, right? Think about it in money and people pay more attention. The way to do that is to put in a scientific notation. If I write 9.0 10 to the third, that is the same number of same numerical value that still represents 9,000, but now I only have 2 sig figs in my number. So we're going to do some calculations in just a sec with sig figs, but oftentimes we're going to have to round, okay? Rounding some people can get kind of funny on their rounding rules. We're going to follow the general consensus of what chemistry textbooks do. And if the first digit to be removed is equal to or greater than 5, we're going to round the number up. If the first digit to be removed is less than 5, we're going to round the number down. So let's round each of these numbers to 3 sig figs. 3, 5, 5 gives me my 3 sig figs, which means I need to cut the number right here. The number that I'm removing first, I don't care about the rest. I only care about that first number removed. The number I'm removing here is a 7, so it's greater than 5. I'm going to round up to 3.56. Second number, 5.52209. I want 3 sig figs, 1, 2, and 3. I'm going to cut the number right here. And now the number that the first digit to be removed is a 2. That's less than 5. I'm going to go ahead and round down. So I get 5.52. Next number, 3.555. 1, 2, and 3. My first number to be removed is a 5. If it is equal to or greater than 5, I always round up. So I'm going to round this up to 3.56. Next number, 3 sig figs, is right here, the 9, the 2, and the 3. So I'm going to cut the number here. The first number to be removed is a 4. I don't care about the 9 after it. I am not going to round the 4. Because I'm not going to round it up to a 5 and then round the number up. I'm not even going to look past it. These numbers do not exist to me, okay? I'm only looking at that 4. The 4 is less than 5. I round down to 9.23. Now this one's a little bit tricky. 1995, 1, 2, and 3. I need to cut the number right here. Sorry, I'm trying to draw on the screen. need to cut the number right here, which means I need to drop a 5, which means I need to round up. But if I round that up, it's going to round up to 2,000, but I need 3 sig figs. I round that 5 up. I round up that 9 because of that 5. Because of the 5, I'm going to round up the 9. The 9 is going to cause it to be 10. Which is going to cause the next one to be 10. Which is going to cause the 1 to turn to 2. I get 2,000, but I need 3 sig figs. The only way to get around that is to use scientific notation. So I'm going to write 2.00 times 10 to the third. Now I have the correct number of sig figs, and now I've rounded it properly. What about when I'm doing sig figs and calculations? Students struggle with the addition-subtraction rule specifically. We ask ourselves, when you're doing addition-subtraction, you need to ask yourself, how precise is each measurement? Is it precise to the tenths place, meaning the first decimal place? Is it precise to the hundredths place, which is the second decimal place? Is it precise to a hundredths place, which is, 3 spots before a decimal place? Meaning is it precise 10700? Is it only precise to here if my decimal place was over here? Okay, where's my number precise to? The answer of your calculation has the same number of decimal places as the least precise measurement used in the calculation. Basically, we can't make something more precise than our least precise measuring device. If I'm using a yardstick to measure the distance of something, I can't then come in and say, this is only 3 inches away, because I'm measuring with a yardstick, okay? I can't make my final calculations more precise than my least precise measurement. So the way students like to do this, and I am fine with, is lining up their decimal places. Let's look at this first example. 29.52 plus 3.001 plus 7,219.5. Line up your decimal places. 2952, 3.001, 7219.5. They line up their decimal places so that when they draw a line here, they can see how precise their measurement should be. Now, when you add these up, you're going to get a calculated answer of 7252.021. But notice my least precise measurement is only precise to the first decimal place, so I'm going to round this number 7252.0. I need that 0 there. I need that decimal place in the point 0. I need to emphasize that my precision is to that tenths position. I can't drop the 0. The 0 is significant. It's important, okay? But I can't go past that because my least precise measurement was only precise to that first decimal place. Another way students will do it, instead of, because personally I'm not very good at lining these up. I don't know why. It's a visual thing for me. It's hard for me to physically line these numbers up. So what I tend to do is I tend to look at the numbers themselves and say second decimal place, third decimal place, first decimal place. This is what's going to limit my answer. When I put this in my calculator, I get 7252.021. I know that my least precise number is that first decimal place because I looked at the numbers above, and I get the exact same answer. So if you're like me and you're not good at lining them up, that's fine. If you are a student who needs to line them up, perfectly fine. Whatever works for you is what's important. Okay. So one thing to note here is this spot up here. It says, important, when you add and subtract, it is possible to end up with more sig figs or less, with more significant figures than you started with, or fewer significant figures than you started with. This is completely possible, and it throws students off. So I can, because remember, addition and subtraction is all about the precision of your measurements. You can actually end up with something more precise or less precise than what you had. Let's show an example. The mass of a beaker containing a volatile liquid was determined to be 25.57 grams. After 15 minutes, the mass of the beaker and its contents was determined again, and this time it was found to have a mass of 25.49 grams. What mass of liquid evaporated? Well, let's visually think about this. We had this beaker, okay? We have a beaker, and we have a solution in here, and the first time we measured it, it weighed 25.57 grams. Now I waited 15 minutes, and now The same system only weighs 25.49 grams. So that means that some of the liquid evaporated away. Some of the liquid escaped the beaker and is now in the gas phase. And that's what evaporated means. But I want to figure out what mass of liquid evaporated. Now, if I put this in the calculator, it's actually going to give me the right answer pretty easily. But it's the sig figs. If I ask a student how many sig figs are in this answer, that messes them up. I have 25.57 grams to start. After 15 minutes, it only weighs 25.49 grams. When I do the subtraction here, this gives me 0.08 grams. Now again, if I plug this in the calculator, it's going to give me the right answer. Just tell me 0.08, and students are going to write that down. But most often, instead of asking for the actual mass, I'll ask you how many sig figs. That throws students off, and I need you to understand what's happening. Here, you had 4 sig figs. Here, you had 4 sig figs. Here, you only have 1 sig fig. And it's because we're looking at precision of our measurement. Our measurement is precise to that second decimal place. It just happens to be that when we calculated it, the final answer here had 1 sig fig left, but we kept the precision of our measurement, and that's what's important. Sig figs in scientific notation really throw students off. And so I'm going to show you a shortcut here. Some of you are going to do it, some of you are not. Some of you are going to come to office hours, and I'll explain it again, and then you'll get it there. If you don't get it, it's okay, okay? There are ways around it, but the shortcut will make your life a lot easier when it comes to doing sig figs in calculations with scientific notation, specifically for addition and subtraction. So first up, we've got this example up on top. 9.2678 times 10 negative 4 plus 8.0 times 10 negative 5. There's 2 ways to solve this problem, a harder way and an easier way. The harder way is to get them into the same exponent form. Notice here I've got one of them as 10 to the negative 4 and one as 10 to the negative 5. I can't compare those. I can look at this and say that this number has 5 sig figs right now. I can look at this number and say this has 2 sig figs right now. That's great, but that doesn't help me because addition subtraction is looking at how precise my measurement is, not how many sig figs I have. So get them into the same exponent. What I mean by that is either take them entirely out of scientific notation or get them into where these numbers are matching each other. Let's go ahead and take them in completely out of scientific notation. The first number is 0.000092678. The second number is 0.00080. When I add these 2 numbers together, I get a numerical answer, 0.001000678. When I line up my decimal places, I'm cutting it right here. So my final answer here is 0.001007 because, again, the first digit to be removed is a 7. I'm going to round up. And I can put that back into scientific notation and say 1.007 times 10 to the negative 3. Okay? I personally think that's a harder way to solve it. Another way to do it would be get them into the same exponent. I can either go to the 4s or the 5s. Let's just go to 4. This would be like 9.2678 times 10 to the negative 4 plus 0.80 times 10 to the negative 4. If I wanted this to the negative 4, it'd be 0.80, not 8.0, because it's one number smaller. Gives me 10.0678, 10 to the negative 4. But again, if I drew that line, I've got to drop that 7, 10.07 times 10 to the negative 4, which we usually wouldn't leave it in notation like that. It looks a little weird for scientific notation. We would report it as 1.007, 10 to the negative 3. There is an easier way, though, and it's thinking about what these numbers mean. But it takes a minute to get it, okay? So you're going to have to be patient while you practice this, and I recommend going through a couple examples like this in the notes here and the additional practice and just kind of making up some numbers on your own and walking through it to see what I mean by this. I'm going to zoom in on the number up here. Let's talk about what all these things mean, okay? I love this function, and at the same time, only when it works. Okay, the -4 here is telling me how precise this specific number is. So the -4 is correlating to that 9, okay? So what that means is that this 9 is at the -4 position, which means the 4th decimal place. Because again, if I took that out of scientific notation, I see I've got 1, 2, 3, 4. The 9 is at the -4 position. This 2 is at the -5. The 6 is -6. The 7 is the -7. And the 8 is the -8. Notice 1 decimal, 2 decimals, 3 decimals, 4 decimals. And as we go decimals, we say they're negative because they're getting smaller. -5, -6, -7, and -8. So just by counting down, I start at 4, and then I can count down 4, 5, 6, 7, and 8. And I can tell exactly how precise this measurement is. Just based on that, I know that this number is precise to the -8 position, which is the 8th decimal place. I have 8.0 times 10 to -5. Similarly, that -5 is going for this 8 specifically. So -5 and -6. And notice 1, 2, 3, 4, 5, and 6. So this is precise to the -6 position, which is the 6th decimal place. If I plug that calculation into my calculator, so I just plug in my calculator 9.2678, look for the E button on your calculators. That's what you should be using for scientific notation. If you're unsure, please come see me. E to the -4 plus 8.0. E, some calculators, most calculators say EEC, some say EXP. Okay, that's what you should be using. That's what you should be looking for on most calculators at least. -5. When I put this in my calculator, I get 1.00678 times 10 to the -3rd. Now I can quickly say, well, I know that this is precise to the 8th, this is only precise to the 6th. This is the least precise. So therefore, my number can only be precise to the 6th decimal place. This is the 3rd, 4th, 5th, and 6th. I'm going to drop that 7, 1.007 times 10 to the -3. Again, 3, 4, 5, 6. My number is precise to the 6th decimal place. And so it's a shorthand by using that scientific notation to your benefit. Let's do another one using our shorthand. 4.5972 times 10 to -9. That means that this is precise to the 9th decimal place. 10, 11, 12, and 13. And I say 9th and 10th and 11th because that's a decimal place. They're smaller, okay? But again, the 13th decimal place. Or that's why I often say 10 to the -9, 10 to the -10, because that's representing decimal places. It means the same thing. 13th decimal place or 10 to the -13 is the same thing. Looking at the 1.2379 times 10 to -7, this is at the 7th decimal place. 8, 9, 10, and 11. This is the least precise. It's less precise than 13. So my final answer can only be precise to the 11th decimal place. I plug this in my calculator, and I get a calculated answer of 1.283872 times 10 to the -7. But again, what does that -7 mean? The 7 is for this position. So 8, 9, 10, 11. I'm going to cut my number right here, and I'm going to round that 7. 7 is greater than 5, so I'm going to round up, and I'm going to round this number to 0.2839 times 10 to the minus 7. I've kept my precision, and I haven't had to worry about undoing the scientific notation. It's slightly trickier when the numbers get bigger like this because you've got to count down first, if that makes sense. So personally, I recommend just taking, if they're this small, I take it out of scientific notation, but we can still do it. This, because it's a positive number, I've got to count down. I can't count up. It's getting smaller in the ones position first. So this is at the second place, this is the first place, and this is the 0 place. What I mean by that is if I took this number out of scientific notation, it's 245. The second place is my 100th, the ones is my 10th, and the 0 is my ones. Plus 2.34 times 10 to the third, 3, 2, 1, same as 2340, okay? The thousands place, the hundreds place, the tenths place, and it doesn't have a value at the ones place. When I add these together, I get 2585, but notice that this is only the least precise to the ones place. The one, which is 10 to the 1, and 10 raised to the 1 is a 10. So it's precise to my 10th position, okay? The 0 position, 10 to the 0, would be like my actual numerical 1, 2, 3, 4, 5, 6, 7, 8, 9. This is precise to the 10th position. So I've got to round here, getting rid of that 5. It is a 5, so I'm going to round up. I'm going to write 2590, or if I want to keep it in scientific notation, that's fine too. I would write 2.59 times 10 to the third. Again, I recommend just spending some time with it and playing with it a little bit. It does make more sense when you get some practice with it, and it really does help make it a simpler concept to do. Okay, most students are fine doing sig fig calculations with multiplication division. This is where most students put their effort, and it's easier to do. So and you do have to be able to do it, and this is primarily what we will be doing throughout the course, yes, but especially in the beginning of the semester in Chem 1, and then in certain spots throughout Chem 1 and Chem 2, we are doing multiplication division, so you can't forget the rules, okay? Multiplication division is the more common one you're going to see. In multiplication division, you ask yourself, how many sig figs are there? How many significant figures does each number have, are present in each measurement? You find the number with the least number of sig figs, and that's how many sig figs the final answer will have. So for example, 2.99 times 7.3 gives me a calculated answer of 21.827. When I look at this though, the 2.99 has 3 sig figs. 7.3 has 2 sig figs. My final answer can only have 2 sig figs, so I'm going to round it by dropping that 8. The 8 is equal or greater than 5, so I'm going to round this up to 22. I need 2 sig figs in my final answer because this is limiting my sig figs to my overall example. Down below, I don't care that it's in scientific notation now. It doesn't make a difference to me because I'm doing multiplication. Here, I have 3 sig figs. Here, I only have 2 sig figs because again, this portion of the question is just telling you how big the number really is. It's not giving your significant figures. When I calculate this out, I get 1,230.6, but I need 2 sig figs. So 1, 2. I'm going to round that number. The 3 is the number I'm going to drop, and the 3 is less than 5. So I'm going to round this to either 1,200, or I could write 1.2 10 to the third. Either one is completely acceptable. They're the same numerical answer. What if I'm doing multi-step calculations? How do we feel about that? Multi-step calculations are definitely going to show up on your assessments, quizzes, exams, etc. You need to be able to do them, and you need to be able to do them properly with sig figs. They are testing your sig figs intentionally. Don't let them trip you up, okay? There are additional practice problems looking at doing these as well. I highly recommend going through them, making sure you're getting the right answers. You need to remember PEMDAS for this, so orders of operation. And then from there, you do PEMDAS first and then do your calculations. Make sure that you're plugging these things in your calculators correctly. Using non-graphing calculators can make things a little more difficult for most students, but make sure you're plugging these things correctly into your calculator and come see me if you need help. Let's look at the first example. I have 12.3 divided by 8.72 plus 295.7. By orders of operation rules, I am going, because the division sign is written as it is, I'm going to do this division first and the addition second. What I'm going to do in my calculator, though, is I'm going to do this calculation straight through in my calculator first. Then I'm going to look at sig figs, okay? So, because I don't want to create round off error. And I'll show you an example of that on the last example here, an example of round off error. When I plug this into my calculator, I get 297.1105505. Calculators don't care about sig figs. They're just going to give you numbers. You are responsible for determining what's important and what's not. So now that I know my calculated answer, let's go ahead and look back at my sig figs. On the 12.3, I have 3 sig figs. On the 8.72, I have 3 sig figs. When I actually, so now I'm going to go back and I'm going to calculate this part by part. When I do 12.3 divided by 8.72, I get a numerical answer of 1.41, okay? I need 3 sig figs in my answer here because the numerator and denominator both had 3 sig figs. 1, 2, and 3. I'm not going to round anyway because I don't want to create round off error. I'm always going to carry an extra digit, but this one just happens to be the correct numerical answer. I'm going to add that to 295.7. Notice here, this is precise to the second decimal place, whereas this is only precise to the first decimal place. That means my final answer can only be precise to the first decimal place. I'm going to drop the 1 here, so I'm going to round this answer to 297.1. The next example, 12.3 plus 897.21 divided by 67.982. Remember your orders of operation. When you have the addition like this in the numerator with the division sign as that full bar there, what that's implying is that you have parentheses there. I don't have to write the parentheses. It's telling me I have parentheses there. It's telling me to do that addition step before I do the division. When I take 12.3 and add it to 897.21, I get a numerical answer of 909.51. Again, I still have not done the second part of that calculation. But let's talk about the first part. The first question, I'm doing addition, so I'm looking at how precise my measurement is. The first number is precise to the first decimal place. The second number is precise to the second decimal place. So my number is precise to here, the first decimal place. I'm not going to round it yet, but I am going to note that I have 4 sig figs in that numerator because, again, that 1 is not significant. I'm going to keep the 1 there because I want to use it in my calculation, but it's not significant in my calculation when it comes to sig figs. My denominator has 5 sig figs. So now when I calculate this out and I get 13.3786885, I know my final answer can only have 4 sig figs. 1, 2, 3, 4. I'm going to drop the 8 right there, and I'm going to round this up to 1338. I'm going to add an extra piece of paper here so that I can write this for you. Okay. Next example, 9.972 times 10 to the negative 9 plus 5.8 times 10 to the negative 11 divided by 4.8 times 10 to the negative 8. So now I'm combining that scientific notation stuff again with my sig figs. I am doing addition in the numerator because it's written as a numerator with that division sign there. Again, that implies that I have parentheses there. I don't have to write them. It's implied in the way it's written. So I need to do the numerator first, and then I'll divide by that value by the denominator. When I do the numerator, I get a numerical value of 1.0030 times 10 to the negative 8. How did I know to put an extra 0 here? When I actually calculated this out, 9, 10, 11, and 12, meaning 12th decimal place. It is 10 raised to the negative 12. 11, 12, 13. 13th decimal place. This is the least precise. I need my number to be precise to the 12th decimal place. 8, 9, 10, 11. The calculator tells me 1.003 times 10 to the negative 8. But it's not precise enough. I need to add a 0 to keep the precision of my measurement. And that's where the 0 comes into play. The 0 here is so that I keep the precision of my measurement. Now I can go ahead and divide that by 4.8, 10 to the negative 8. Now I'm doing division, so now I'm looking at number of sig figs. My numerator has 5 sig figs. My denominator only has 2 sig figs. So when I calculate this out, I'm trying to figure out where to write this, I apologize. When I put this in my calculator, I get an answer of 0.208,958,3333. But I know my final answer can only have 2 sig figs, so I'm going to round it to here, 2 sig figs. The first number I'm going to remove is an 8, so I'm going to round this up, and my actual answer here will be 0.21. So in this example, it didn't really matter that I added the 0 here, but if I had asked you that numerator and asked you for the numerical answer there, that 0 would have mattered. So we need to make sure that we're always including it because it may matter in the question. Now this last example here is very intentionally done to show you what I mean by round off error. I keep telling you I want to avoid round off error, but what do I mean by round off error? If you round too early, you will create round off error. What I do when I'm doing calculations is I track my sig figs by underlining where my sig figs are and carry 1 digit past that point until the very end. And when I report my very last answer, I round my answer at that point. So let's show you what I mean. 31.49 minus 12. This gives me a numerical answer of 19.49, okay? But the 12 is only precise to the 1's position, so only precise to here. So theoretically, I should round that and say 19, right? Based on the sig fig rules, that number is 19. It's no longer 19.49, it's 19. When I do the 434.049 minus 432.1, the numerical answer here, 1.949. Now, subtraction here, this is precise to the 3rd decimal place, but this is only precise to the 1st decimal place. So this is only precise to the here. I should technically round this number to 1.9. But if I finish the calculation, plug it in your calculator and check yourself. If you take 19.49 and multiply it by 1.949, you get a numerical answer of 38. If you take 19 and multiply 1.9, you get a numerical answer of 36. The mistake made here is we rounded too early. So in this case, if I had carried an extra number and did like 19.5 times 1.95, knowing that that 5 was not significant, I would have avoided the round off error. But rounding too soon can create round off error in your measurements, and you need to be careful and cognizant of that as well. So I recommend carrying 1 or 2 extra digits until the very last answer, because my actual answer here is 38. 38 is much more accurate than 36.